Okay, so I'm calling this a future of ensemble forecasting, but it's not really that. It's just a summary. The future of ensembles may be a better way to say it, but anyway. Using Earth system models is considered one of the ways where obviously you are going to add more and more complexity. Does that mean it'll become more accurate? This is a critical question. My own favorite is to really try to figure out whether just increasing model resolutions without having all the Earth system components is the best way to seek higher skills, or is it that there are certain feedbacks in the Earth system which are going to give you skill rather than necessarily increased resolution? Increased resolution is always pointing to these processes we mentioned about upscale kinetic energy propagation, our fronts and features and patterns and so on, but there are critical feedbacks missing, for example from vegetation to clouds and precipitation. Then can you ever get it right if you don't have proper representation of vegetation? So Earth system models presumably can do that, and also that will automatically expect that it will lead to seamless forecast systems, because if you have the Earth system model as a requirement at S2S timescale, you will essentially have to think of running the same model out to the longer timescales as well, and maybe also to the weather timescales. The other thing that we mentioned is the data assimilation and how critical that is for ensembling and for reducing error growths and other things. Ensemble spread or ensemble model uncertainties and so on. Okay, I'll leave it there. So this is from ACMWF, schematic representation of different configurations of a coupled data assimilation system. So data assimilation we talked about. Typically for climate forecasts, ocean is initialized with all the assimilations, and the atmosphere is allowed to evolve over climate timescales with the assumption that we are in the predictability of the second kind, so ocean is going to force and be a boundary value problem. Whereas in the weather forecast we typically have the prescribed ocean, and we are assimilating into the atmosphere and giving initial conditions in the atmosphere, which is critical for few days of weather forecasts. So coupled assimilation here basically means the different colored bricks represent different Earth system components. For example, red the atmospheric 4D VAR assimilation, blue the ocean assimilation, while the sea ice assimilation, and green so white is sea ice, green is land. The right hand configuration in which the components are all aligned with the atmospheric 4D VAR represents a strongly coupled assimilation system. The left hand configuration represents a weakly coupled assimilation system. Here the bricks are differently sized to represent the different assimilation methods, and the components can overlap to reflect the lag in the observation information passing between the components. Okay, so you don't update the, for example, sea ice, land, and ocean every time step when you are doing atmospheric integration as the dominant, let's say, weather prediction or even S2S prediction. Many models do S2S prediction with just the atmospheric model without coupling. So that's the idea here, whereas here it's strongly coupled, so the whole system is being updated after being assimilated together. There is also now coupled reanalysis, like the CFS coupled forecast system reanalysis by NOAA, which does the coupled system forecast. It's not an Earth system in the sense of what is implied here, but it is a coupled ocean, atmosphere, land system model. To summarize then, initialization is important and influences performance in the early forecast ranges. We already saw that, which is where the data assimilation becomes critical. Ensembles provide more complete and more valuable information than single forecasts. There is no unique way to generate ensemble forecasts, either in the way that initial and model uncertainties are simulated, or in the ensemble configuration. For example, number of members, forecast length, resolution, and frequency. Okay, so each center chooses different ways to do it, but we have to think about the consequences when you do multi-model ensembling. And ensemble's reliability and accuracy depend on the quality of the model and the initial conditions, on the resolution and number of members, and on the methods used to simulate initial and model uncertainties. Again, data simulation is a critical part of the initial uncertainty simulation. In the future, we expect ensembles to include more and more relevant processes and move towards an out-system approach to modeling and assimilation. We also expect an evolution towards a seamless approach in the design of analysis, medium range, and S2S ensembles. Okay, that's kind of the conclusion of this chapter on ensembling. And we'll now move on to something more specific in terms of representing cloud processes and how that affects MJOs in the model in terms of simulation and forecasting.